Okay, our next speaker is Dr. Megan Ansdell. Megan is well-traveled, so I'm going to cheat here. Make sure I get all this. So Megan grew up in Hawaii, went to St. Andrews in Scotland for undergrad, which is not typical. Then she got a master's degree in International Science and Technology Policy at George Washington University. Then came back to Hawaii for grad school, get a PhD. Where she did a few different projects, none of which she's working on now. She went postdoc at UC Berkeley and is now at the Flatiron Institute working on machine learning. So we're looking forward to hearing about some of this.
I'm not going to talk at all about machine learning. I'm sure you're all tired of hearing something neural network, so I won't talk about that. So thank you to the organizers for inviting me here to talk about some of the work I've been doing with planet formation. I think the only thing worse than being put in front of in between the audience and lunch is between the audience and happy hour, which is where I currently stand. So during this talk, if you have any questions or thoughts or comments, just feel free to interrupt me. I think it'll be a lot better than me just talking at you for 40 minutes. But today I'm going to talk about what we've learned about planet formation from ALMA and Kepler. So ALMA and Kepler are two very different facilities. ALMA is a radio interferometer. Kepler is a space-based mission that does time series photometry. But hopefully I'll show you today that these two data sets are actually very complementary, and we've learned a lot about planet formation from them. There we go. Okay, so to start, just some basics of planet formation. So planet formation starts with star formation. So you begin with a prestellar core that's on the order of tens of thousands of AU. This is sort of time zero, and it starts to collapse. Very quickly, much less than a million years, you get what's a class 0, class 1 source. So this is basically a disk that's still forming, and it's still embedded in its natal cloud. And you have scales that are on the order of about 10,000 AU at this point in time. Then for the next about 10 million years or so, you get a class 2 source, which is also known as a protoplanetary disk. So this is a disk that is made of gas and dust. It's in Keplerian rotation. It's around a pre-main sequence star. You might see some jets, and it's getting to the scales more of our solar system at around 100 AU. And then for the next few hundred million years, you get debris disks or class 3 sources. These are second generation dusty disks that don't have a lot of gas in them. And this is where sort of terrestrial planets are figuring their stuff out. And then finally, you get a planetary system like our solar system that lasts, on the order of gigayears. So today I'm going to talk to you about this phase, the protoplanetary disk phase. So there are a couple of great review articles on the observational and theoretical side of protoplanetary disks, if you want to learn more of the details. But basically, these things last for about 1 to 10 million years. They're called protoplanetary disks because they're thought to be the sites of planet formation. We don't know when, though, within that 10 million years, that planets are actually forming. This is what we're trying to figure out. So this is a schematic of a protoplanetary disk. You basically have a optically visible pre-main sequence star in the center, which is great because you can do things like measure spectral types and get mass accretion rates and get stellar masses. And this is the main heating source for the disk, so you have a temperature gradient in the disk. So in the outer regions, the disk is very cold, so this is why we use radio wavelengths to study this area. And this is where most of the mass that's available for planet formation is going to be located. And then in the inner regions, it gets warmer, and so you start using things like near-infrared and mid-infrared observatories to look at that. So that's basically what a protoplanetary disk is. One of the things that we use to study protoplanetary disks is ALMA, or the Atacama Large Millimeter Array. We've heard about ALMA observations a few times today. So ALMA is an interferometer. It's made of 66 mostly 12-meter antennas that are located in the Atacama Desert at 16,500 feet. It's an interferometer, so all of these antennas work together to provide better resolution and sensitivity than you would get from just one single dish. And the maximum baselines, or the maximum distance between these antennas can be up to 15 kilometers or so. So this is a really amazing facility that was much better than previous interferometers, and so it's giving us orders of magnitude sensitivity and resolution than we got before. And anytime you do that in any sort of field, you're going to really revolutionize any science field that these facilities are providing observations for. So ALMA has been really great, and one of the things that ALMA has been doing is to provide very high resolution and high sensitivity observations of protoplanetary disks. So this is one of the disks from the D-SHARP survey, which we've heard of before. Ian showed some of the images from this survey as well. So these are incredibly beautiful images that have just been blowing our minds. But it's been able to provide this detailed structure, but the integration times are long. So typically an hour per target to get observations like this. And we're not looking at typical disks. We're looking at the biggest and brightest disks that we can get our hands on. So these images are great, but they're providing biased views of the protoplanetary disk population. So there's another way to use ALMA, which is to take advantage of its sensitivity and do large-scale surveys that can look at an entire star-forming region. So we can still probe fundamental bulk properties when we do this. The integration times are now a minute a target, so you can look at hundreds of disks very, very quickly. And you can look at entire populations of protoplanetary disks in star-forming regions and start to get an idea of what is going on a population level. So these are what we've been calling demographic surveys or population surveys. So why should we be conducting these demographic surveys? I kind of mentioned the idea of getting over the biases that you get in other surveys. But these are the sort of images that we get out of these snapshot surveys. They're very blobby, and you kind of think, why would we go back to staring at blobs? Why go back to the Stone Ages when we have ALMA now? One of the reasons, again, is this overcoming biases. Another thing is that when we observe these disks, we have to go from the observables to some physical property, and we have to make assumptions when we do that. So if you want to sort of tease out correlations in physical properties, sometimes you need to get entire populations, large samples, if you want to find these correlations. And then another reason, which I'll talk about a lot today, is that we can look at populations of different ages and see how these disks evolve with time. And this will give us a better idea of disk evolution and planet formation. So this is what we've been doing with ALMA over the last few years. We've been looking at star-forming regions of different ages and trying to look at the entire population and see how that changes with age. So I'll focus on these three regions today, but there's been a bunch of other surveys that have been done as well that I encourage you to look at. But we looked at the Lupus region. It's a series of clouds that are about 1 to 3 million years of age, so this is a young region. Then we looked at Sigma Orionis, which is on the order of 3 to 5 million years. This is a middle-aged region. And then finally, Upper SCO, which is a more evolved region at 5 to 10 million years of age. And we're combining these to see how these protoplanetary disk populations evolve with age. Okay, so what can we measure with these surveys? There's two things that we've been focusing on currently. One of them is just the mass of the disk, which sounds really easy, but as I'll show you, is very hard to measure. But the way we do this is, if we want to do it very simply for large populations, we look at the millimeter flux, which gives us the dust mass, and then we can measure certain molecular lines to get the gas mass. And this is telling us basically how much material is available for planet formation. So millimeter continuum emission is fairly easy to measure, so we get these for about 80% of the sources in our sample will be detected. For gas, this is much fainter emission, so we only get detections for about 20% of the sources in these typical snapshot surveys, and the rest are upper limits. The other thing we look at is radius, so how big are these sources? Again, for the dust, you look in the millimeter, and for the gas, you look at molecular emission. I'm not going to talk too much about the radius. I'll focus on the mass in this talk. Okay, so how do we get dust masses? So with ALMA, you can get hundreds of dust masses in a matter of hours, which is pretty amazing. Before ALMA, this took a thesis. My academic brother did this for his thesis, and it took him a very long time. He was a little upset when we can do this with ALMA in 2 hours. But this is the way that we do it. So you can make very simple assumptions that allow you to basically have a linear relation between the submillimeter flux that you measure with ALMA to get a dust mass. So to do this, you have to assume optically thin millimeter flux, which I was hoping to brush under the rug, and then Ian brought up the problem with opacity. Thanks, Ian, or optical depth. But you can sort of assume-ish that it's optically thin. You can get a distance, which is much easier now with Gaia. You can assume a temperature for the dust in the outer disk, which is what we're probing with ALMA. We assume 20 Kelvin. And then you have to assume also a dust opacity. So if you get sort of nervous with all these assumptions, you can join the club. Everybody is sort of nervous about this. But you can also check this with more complex models that take into account radiative transfer and optical depth. And basically you get to within a factor of like 2 or 3 with those other more detailed methods. But the idea is you have large samples, so this kind of uncertainty is acceptable. This is just the dust mass, though. If you want to convert this to a disk mass, you have to do just a tiny extrapolation of 2 orders of magnitude because I mentioned that these disks are made of dust and gas, but at least at young ages, they're mostly made of gas. They're 99% gas, 1% dust. But again, the gas is so difficult to measure that we typically look at the dust. And you also have to assume that the dust that you're looking at with ALMA, so ALMA looks in the submillimeter and the millimeter, and so it's probing mostly dust grains that are about that size, submillimeter, millimeter, centimeter size. If you assume sort of typical grain size distributions, this is a fair assumption that most of the dust mass, at least, is in the millimeter grains. So this is how we get dust masses with ALMA very quickly for large samples. So when you do that for an entire region, you can do things like plot a cumulative distribution function. This is actually a Kaplan-Meier estimator, which is a statistical method, survival method that takes into account upper limits, which we have in our sample. You can plot a cumulative distribution function and compare the different regions to see how these distributions are evolving. So this is a distribution for the Taurus star-forming region, also young at just a couple million years of age. This was done prior to ALMA, mostly with the SMA. And this is the average dust mass in the region, which is about 15 Earth masses. So when we looked at the Lupus star-forming region, which I mentioned before, which is of similar age, we did this with ALMA, and we can plot the dust mass distribution, and it looks very similar. So this was all made sense. Lupus is also a low-mass star-forming region. It's also on the order of a couple million years of age. So that made sense. When we look at the middle-aged Sigma Orionis region, which again is a little bit older at 3 to 5 million years of age, we see a more evolved dust mass distribution, makes sense. And then we can plot upper SCO, which is at the end of sort of the disk lifetime, and again you see a more evolved disk population. So this, seems, makes sense, but before ALMA we actually couldn't show this statistically. And so what you're seeing here is not just the disk dispersing, you're seeing grain growth, presumably into planets. So as I mentioned before, ALMA looks at millimeter and submillimeter, centimeter size grains. When things grow to bigger things like planetesimals, we no longer can see that mass. So the disk is dispersing, but also planets are growing. The problem is, though, you can't really tell the difference based on just ALMA observations. But one of the things you can do is compare this dust mass distribution to some value that you can compare then to the exoplanet population. So here I'm picking 10 Earth masses because this is about the core of a giant planet, or a few super Earths, which are the most common type of planet that we see in the exoplanet population. And all I'm doing is reading off of this plot how many of the disks in each region have masses that are of equal or greater than to 10 Earth masses. And even by just a couple million years, only a quarter of disks have this amount of raw material available for planet formation. And you can see it declines very rapidly with age. So these numbers are very close to giant planet occurrence rates and well below super Earth occurrence rates by sort of a couple million years of age. So this is telling us something about how quickly planets are forming. We can do a more direct comparison to the masses that we see in the exoplanet population. So this was some work done by Carlo Manara, who's at ESO. But he took the dust masks that we're seeing in disks. So this is disks that are around a couple million years of age, again, so young, pretty young disks that are plotted in red. This is mass as a function of stellar mass. And then compared this to the cores of exoplanets that we see that are fully mature. And we were expecting this to be flipped. But what it shows is that it seems like even at the age of just a couple million years old, we can't account for the exoplanet population. So this is again telling us that planets must be forming pretty early on. There's a bunch of caveats to this, which I'm happy to talk about later with anybody. But as I'll show in the rest of the talk, there are a few, I think, other lines of evidence that are supporting this idea of rapid planet growth. Okay, so everything I've talked about so far has been derived from the dust. So again, just as a reminder, protoplanetary disks are 99% gas. So we can talk a little bit more about the gas side of things. And again, we measure dust just because it's bright, it's easier to measure. Gas is more difficult to measure. Okay, so if we look at the gas, because it's so much fainter, we end up not getting 100 disk masses in 2 hours with ALMA. We get more like 30 disk masses. But it should be a more, if we're measuring gas masses correctly, it should be a more direct probe of the actual mass of the entire disk. The problem is that H2, which is the main component of gas in a disk, is really, doesn't emit efficiently at all at millimeter wavelengths because the disk is too cold. So instead we use carbon monoxide and in particular optically thin isotopologues so that we can actually trace the gas mass. And we used a grid-based modeling approach which makes this quick. So this is work that Will was actually involved in back when we were both in Hawaii. And more detailed modeling has been done by Anna Miatello along these same lines. But the idea is that you have a disk and you're modeling the CO and you take into account things like photodissociation and freeze out, but you can predict basically gas masses by just measuring C18O and 13CO. And so if you make a grid of models, assuming a variety of different and reasonable sort of disk properties, the main thing that matters with these two lines is actually the gas mass. So when you plot the grid, they actually separate out fairly nicely. And you can just measure these two things at the telescope, overplot them on the grid, and you get a decent-ish estimate of gas mass. So when we do that for lupus, again, a very young region, we see that the gas masses are on the order of about a Jupiter mass or less, even at these young ages. So again, this evolution in the material that's available for planet formation is happening very quickly. So one explanation for why this gas is being dispersed so quickly is that as dust grains grow, they settle towards the midplane of the disk, and you get this gas-rich atmosphere, which is then preferentially removed by a variety of winds, which we're thinking are becoming increasingly important, or is accreted onto the star. There's another side to the story, though, that's been looked into a lot in the last few years. And that is that we're not actually seeing a depletion of gas, but we're seeing a depletion of volatile carbon. So as I mentioned, we don't measure H2 directly. We use a proxy of it, which is carbon monoxide. And if that carbon is being preferentially depleted, then we're not actually looking at the total gas mass. So there's a variety of mechanisms that have been proposed theoretically to deplete volatile carbon. And there's been a lot of ALMA proposals in recent years to try and actually observe this volatile depletion. So this is really interesting. Whatever is happening to the gas is happening very quickly, but we're not sure if it's physical or chemical, although it's probably a mixture of both. So everything that I've been talking about so far has been sort of imagining that planet formation happens in a nice little bubble, but there's loads of external influences that can impact disk evolution and planet formation. So one of these is external photoevaporation. So this happens when you have a OB star that is nearby and can strip material off from the disks. So this is what is responsible for the iconic proplyds that you see in the Orion Nebular Cluster. So you see these disks that are being irradiated by a source and have this sort of tadpole tail down the back. So this is a classic example of external photoevaporation. And the idea is that you have this OB star and then a region where extreme ultraviolet emission dominates, where mass loss rates are very high. And then there's a FUV-dominated region where mass loss rates are a little bit lower. And then at some point, this OB star doesn't affect disk evolution anymore. So this was first looked at using very early ALMA and also SMA data by Rita Mann in the Orion Nebula Cluster. This is a very, very young region, at just about 1 million years old. And what she found is that you had to be very close to the OB star to see an effect on mass of the disk. So if you were 0.03 parsecs from the OB star, you would see this lack of massive stars. And then in the FU region and beyond, basically disk mass distributions look the same as if you were in a low mass star forming region. So the conclusion was just that you didn't have to worry about external photoevaporation unless you were very close to the star. This changed a little bit when we looked at Sigma Orionis, which has an OB star in its center. This is a little bit older, so basically there's been time for external photoevaporation to have an impact on disk evolution. And also, the Orion Nebula Cluster has a lot of intra-cloud material, which is probably protecting the disks. And there's no more cloud material in Sigma Orionis, so they're being more directly irradiated. And so we again see this sort of lack of massive disks, but instead of 0.03 parsecs from the star, it's half a parsec from the star. And then you also see a trend with disk mass all the way out to the cluster edge, out to 2 parsecs. And we didn't have many gas detections in this region, only in the very outer regions. And this is all consistent with external photoevaporation having an impact on all disks in a cluster. So this is another thing that we need to think about that people are starting to look into a lot more now and include in their modeling. The other external effect that I haven't talked about at all is binarity. So, at least about half of stars are in binary systems, and we know that this impacts disk evolution. So this was looked at in Taurus and showed that binaries that are less than about 3 AU in separation will have a decrease in millimeter flux, which is likely due to these tidal truncation of the disks. So binaries will have less material available to create planets. More recent work out by Scott Barenfeld looking at upper SCO, so the older region, showed that by the age of upper SCO, binaries and single stars actually had the same millimeter flux distribution. So perhaps early on, binaries have a big effect, but by the age of upper SCO, basically disk evolution is the same. However, we still do see an effect on the exoplanet population with these same binary separations. So this again, I think, points to planet formation happening more on these time scales than these time scales because we do still see an impact from binarity in exoplanets. Okay, so there's a lot going on here. How can we ever hope to interpret this sort of diverse observations that we're seeing? As we saw in the previous talk, we have this wonderful thing called the solar system that's right at our front doorstep that we can use to perhaps calibrate and help interpret what we're seeing. So again, what we're looking at with ALMA is millimeter, submillimeter, sort of centimeter size grains. And this is analogous to the chondrules and CAIs that we see in meteorites. So these are similarly sized objects. We can date these very precisely in our solar system. And what we see is that they tend to be also on the age of a few million years. So great, that makes sense. We see in protoplanetary disks grains that are of this size. We also see them in our solar system. However, we're not just dating these. We can do things like date larger bodies in our solar system. So also from meteoritic evidence, we think that Jupiter's core, which is 10, 20 Earth masses of dust, formed within 1 million years. And we also know that asteroids were forming on the time scale of a couple million years. So, I mean, this sort of makes sense. Why would you grow millimeter or centimeter sized grains and then wait for a little while before building other things, right? Everything should be sort of happening together. So we have pretty clear evidence from our solar system that larger bodies were forming on the same time scales as these smaller pebbles. So does this mean that the fact that we're observing very clearly millimeter sized growth in protoplanetary disks means that we're also seeing planetesimal growth? And I think just in the last year or two, the community seems to be converging on this idea, and we're starting to propose observations for earlier phases, not just at the protoplanetary disk phase, to try and see if this is true. So I'm going to need to rename my thesis Postplanetary Disks, I think. And we need to start looking at these protoplanetary disks as perhaps evidence of planet formation already being done or close to done, rather than signs of actual ongoing planet formation. Okay, so to summarize the ALMA sort of part of the talk, the demographic surveys that we've been conducting have focused primarily on masses and sizes, and I talked mostly about masses today. This has been providing insights into disk evolution and planet formation, and I think when you combine this with the meteoritic evidence we have from our solar system and with exoplanets, it's seeming to suggest that planet formation is much quicker than we initially thought on the timescales of 1 million, 2 million years. So I think this will be a pretty big focus of our research in the coming years. Okay, so that was the ALMA side of the talk. For the second side, I'm going to focus more on what we've learned from Kepler and K2, and also what we've learned by combining Kepler and K2 together. So to go back to this image of a protoplanetary disk, ALMA basically looks out here. Even at the highest resolution of ALMA, we are not looking at things on scales of an AU. For most disks, it's very difficult, if not impossible, currently to directly observe the disk at less than 1 AU scales. And this is a little disappointing because we want to learn how things like Earth formed and Earth orbits at an AU. So how can we do this indirectly? One of the tools that we can use is Kepler, and in particular K2. So Kepler, K2 is the second mission of Kepler. So Kepler had 4 reaction wheels originally. 2 of them died. I heard that company that made the reaction wheels went out of business. But those 2 reaction wheels died. Kepler could not point efficiently anymore. So some very smart people figured out that you can use the solar radiation pressure as a 3rd reaction wheel to stabilize Kepler's pointing. But then Kepler needed to look along the ecliptic plane, and also could only look for timescales of 80 days before it needed to change its orientation to keep using the solar radiation pressure as a reaction wheel. But the great thing is that there's loads of there's loads of young star-forming regions along the ecliptic. And so we could get very high precision, high cadence, continuous time series photometry of young star-forming regions that span this age of the disk lifetime, the protoplanetary disk lifetime of 1 to 10 million years. And because the cadence was so high, we can actually probe Keplerian timescales that correspond to this inner region of the disk. So we can actually look at changes in the stellar brightness of the star disk system brightness on timescales that correspond to this inner disk. So one of the classes of young variables that allow us to study the protoplanetary disks with Kepler and K2 are what are known as dipper systems. They're called dippers because they have dips in their light curves, and we're not very creative. But the dips are the defining feature of the light curve. So on the left are 3 examples of dipper light curves taken by K2, and on the right are their phase-folded light curves. So you can see some of the dippers are what we call quasi-periodic, so they happen on a regular period. But from epoch to epoch, the shape and the duration of their light curve, of their dip can change from epoch to epoch. There are also quasi-periodic dippers that don't necessarily look periodic until you phase fold them on the detected period. And then you see that the dips do occur on a regular period. So something is changing on the timescale of a few days. And then there are dippers that are completely aperiodic, they're completely episodic. So all these dips, they're very deep, so they tend to be tens of % in flux, up to about an order of magnitude. They're moderate in duration. They tend to last about a day. And when they are quasi-periodic, the periods are on the scale of a few days to up to 10 days. So this is on the same scale of about a stellar rotation period for young stars. Dippers as a population are pretty normal T Tauri stars. If you ignored their light curves, they would just look like normal late type K and M type T Tauri stars. They're fairly common. They make up about 20% of young star forming regions when we're able to sample entire regions. And they all host protoplanetary disks. So it's clearly related to dust that is obscuring the disk in these systems. So the theory that was put forth for these dippers goes back to 1999. This theory was primarily built on one dipper, so the original dipper, which is AA tau. And the idea is that you have a star that has a disk, and the magnetic field is slightly misaligned from the stellar rotation axis, so that when the magnetic field truncates the accretion disk, the symmetry is broken, and you get a non-axisymmetric stream or warp, and material flows from the disk onto the star. And so you get this warp here, and as the star disk system rotates, you'll get this regular occultation that causes the dimming events. And in this case, you need a disk that is viewed nearly edge-on. So nearly edge-on so that you see the occultation, not completely edge-on because the disk midplane is optically thick and you would actually block out the entire star. You wouldn't detect it in your surveys. So this was the view of dippers. It was seen to be something that was fairly common because we detect so many of them, but as a geometric effect. Basically, all young stars with protoplanetary disks would sort of look like dippers if you were seeing them at the right inclination angle. And the difference between the quasi-periodic and the aperiodic dippers was basically explained by different accretion regimes. So stable accretion regimes gives you these nice two stable funnel flows, and you get the quasi-periodic dippers. In unstable accretion, which is associated with fairly high mass loss rates, you get these streamers onto the star that can form and break on the timescale of a stellar rotation period, and so you get these aperiodic dippers. So that was the overall picture of what explained the dippers. Let's see. Oh yeah. Okay. So I had a hard time explaining what dippers should look like to people. So I got a friend of mine who is very skillful at Google Tilt Brush, which, has anybody heard of Google Tilt Brush? It's a virtual reality painting tool because it's Google and they're ridiculous. And it's actually really cool. You put on a virtual reality headset and you paint. This is really hard to do. I tried to paint. It's really difficult. But a friend of mine drew a dipper. So this is what it looks like. Let's see if I can get this to play. There we go. So you can see how as the star disk system rotates, you could get things that occult the star. So this is just him, I think that's him. You can see like the controller, just walking around and filming it. But this is actually a virtual reality environment. So if you have a virtual reality headset, you can walk into the system and like stand under the star and see the accretion columns, and like, it's really cool. Yeah.
Like the ALMA image that Ian showed, is this like a similar stage of the?
It should be about, well, I'm not sure which image you're referring to.
Well, I guess you kind of had the streamers, right? Maybe just like two.
The stars and the systems are about the same age. The science image that I showed was you're talking two stars inside of a circumbinary disk that's probably the size of a system like this. It's
Yeah.
much smaller scales.
Yeah.
Both time scales and spatial scales.
Mm-hmm. Okay, so back to boring plots like this, sorry. So this was the general idea of a dipper. Everybody was happy with it. I was happy with it. And it was tested it was created for the original dipper AA tau, and then these light curves are from Corot, which looked at NGC 2269, which is a young star forming region that's quite far away. I think it's at like 800 parsecs or something like that. But when K2 came along, we started looking at closer star-forming regions that spanned a larger age range. And two things stood out. One, a lot of dippers, most dippers, at least in the K2 sample, are not significantly accreting, which is a problem if you need an accretion disk to explain your phenomenon. So we did things like look at H-alpha emission and Paschen gamma emission for a lot of the dippers and compare it to typical things that are used to classify classical T-Tauri stars that are accreting. And these dippers all end up sort of on the low end of accretion. Another thing we could test by combining the K2 data with ALMA data is to see if these dippers were actually all really in this nearly edge-on configuration. So I think it was like halfway through my thesis, and I was like, I'm just going to check that they're edge-on, because we should. And I looked through the ALMA archive for dippers that just so happen to have resolved observations, and I found an edge-on disk, a face-on disk, and an intermediate disk, which suggested to me that dippers weren't really had to be edge-on. So these are the K2 data, and these are the ALMA data. And this is a really interesting case. This is J1604. It's a pretty famous disk. This is the ALMA image. The ring is actually a lot thinner than that. It's just the beam that's being convolved in. But this is a very face-on disk. That's 6-degree inclination. So this is the scattered light image that I think was taken with Subaru. So the scattered light image is looking at the surface of the disk and small grains. ALMA is looking more in the midplane of the disk. But if you look at the scattered light image, you see a thin ring, but you also see these two sort of nulls here. And this is actually something that is seen a lot now in scattered light. Yes? Oh, 5 minutes, okay. It's seen a lot now in scattered light. And the idea is that you have an inner disk that is inclined, sometimes up to almost 90 degrees relative to the outer disk. And so you get shadows that you see in scattered light. And so this could explain J1604, where you have an inner disk that's being sort of broken and warped, possibly from a companion. So that would explain the intensity nulls and also the pretty extreme dipping events that are happening in the system. Okay, so one of the things we did after that was try and get as many disk inclinations as we could with ALMA of dippers. I won't go into this in too much detail, but basically all you need to know is that ALMA doesn't actually measure all these pretty images that you see. ALMA measures complex visibilities, which are measured in Fourier space. Nobody likes to hear those words, so we show these pretty images. But it's actually kind of important. So when you measure these visibilities, you're taking discrete measurements in Fourier space, and then you're trying to convert this to an image. But because these are discrete measurements, that conversion is imperfect. Also, when you do that conversion, you correlate your errors. So if you want to get a robust measurement of something like a disk inclination and also actual reliable uncertainties, you want to do your analysis in the visibility plane. So this is computationally expensive and annoying for a variety of reasons, but my wonderful colleague Marco Tesari, who's at Cambridge, put together this great package called Galario, which speeds this up a lot and makes it a much more pleasant experience to fit visibilities. So it uses GPUs. How many people here are familiar with GPUs? Yeah, okay, yeah. So they make life a lot better in various ways, including speeding up your computation of synthetic visibilities. So Marco put together this package. It works with GPUs, but it also works with multiple CPU cores. You would literally just do import Galario.CUDA or something like that rather than import Galario, and you get a GPU. Galario is also great because it's very modular, so you can use this to compute your visibilities, and then you can combine it with basically any statistical tool that allows you to explore parameter space. We used MC, which is very popular, made by Danforth and Mackey, to explore the parameter space. And so we can fit the visibilities and also get out posterior distributions and uncertainties. So we did this for as many dippers as we could find with ALMA. We ended up with a sample of 24, all identified by their K2 campaign 2 light curves in a systematic way, and all the disks were resolved by ALMA. So this is what they all look like. And when we plot their distribution of inclinations, we get something that's basically isotropic. So isotropic distributions will be flat in cosine I, which is being plotted here. There's a dearth in high inclinations, and this again is just an observational effect. The disk is basically blocking the star, so you don't detect these. We took advantage of the posterior distributions that we had. So this is an empirical cumulative distribution function of the dippers in our sample, using a sort of Monte Carlo approach of sampling the posterior distributions. And this is compared to a uniform distribution for inclinations less than about 75 degrees. And you can see they're very consistent. So it looks like dippers are not biased towards nearly edge-on orbits. They show a completely isotropic distribution. The big caveat, though, is that this is ALMA. So we're looking at the outer disk on scales of about 10 AU. A few of the dippers in our sample overlapped with the D-sharp survey, which looked at disks at 5 AU scales. So this is basically the best we're going to get with ALMA for a while. D-sharp showed that basically, disks are very diverse when you look at them with high enough resolution. And the dippers basically reflect that. So these are the 4 dippers in our sample, and you can see they all look very different. So again, dippers don't seem to be special in any way, at least when you're looking at the bulk or outer disk properties. So I think what we've basically learned from these objects are, one, space-phase light curves are this wonderful, unique probe of the inner disk region that's otherwise difficult or impossible to probe directly. But they seem to suggest a very dynamic inner disk environment that seems to be completely unrelated to the morphology of the outer disk. So we can't be using this outer disk as a proxy for the inner disk, which is unfortunate because the inner disk is where terrestrial planets are forming. But there's a lot of work going on now to try and use indirect methods of probing the inner disk. And I think there's going to be a lot of interesting stuff coming out of there, especially with regards to using scattered light images from observatories like SPHERE. So I'm out of time, and I'm happy to take any of your questions.
Thank you, Megan. Questions? Yeah. Yes, Justin.
What? That was like very so you showed, what I thought was kind of surprising was that like most of those disks have not actually all that much mass in them.
Yeah.
That's kind of interesting. Even for the very young clusters, very few of them had like a mass linear worth of material in them. And you sort of implied that was maybe a sign for this really fast planet growth. But I've been under the impression that like that was also true even at the earlier envelope stage, where like very few envelopes had that much material as well. So I was wondering like if you had thoughts about that.
Yeah, so Patrick Sheehan is the person that's been sort of
Who I get this.
Yeah, and so I'm not sure if this is published yet. I think he's still working on this. So he looked at Taurus for a limited number of class 1 disks, but the sample wasn't very large, so they went back and tried to get more observations, and he has like hundreds of thousands of hours on supercomputers to try and get disk masses, because it's harder because they're optically thick. So he is actually finding like significantly larger disk masses that are more consistent with what you would expect from like a minor-mass solar nebula or something like that. So I think that's really interesting, and I think it's further suggesting that planet formation is happening at these very early ages. So.
So I think part of the confusion here is that we're jumping from millimeter-sized grains to planets. I mean, all we really know is that there's a certain population of these grains, and we know that from the earlier stages, the grains are growing constantly and changing their distribution. So we're taking this little, image of what we've got, because we've got ALMA, great. But I think extrapolating that to say what the mass is of solid material is the problem.
I agree.
As you know.
Yeah.
Because the CO is doing strange things. So I think we have to back up from the idea that we really know these masses very well, and admit that some of that stuff is in more complicated forms like rocks and boulders and pebbles and so forth.
Yeah. When I say disk masses.
Planetesimal happens fast.
Yeah.
That's correct. We say planets happen fast. That's a little more.
Sure.
Dicey.
Sure. Yeah, I think we would have to rely on our models of planet formation to know how quickly we go from planetesimals to planets. Yeah. But there are, you see, there's a lot of observations of, these wonderful gaps and rings, and people are trying to model them with planets. I think the problem with that is that you can't prove people wrong when they suggest that planets, like X amount of planets have formed these amount of gaps, because we can't actually detect the planets. So.
One more quick question. Happy hour time? Let's thank Megan again.